Hi, I'm Jessica Kittner, and in this video I'm going to explain the concept of electric flux. Flux in everyday usage simply means the flow rate per unit area. In physics it has a more specific definition. The symbol we use is capital Phi, and sometimes you'll see it with a subscript E. Later on in the course you're probably going to see a magnetic flux as well, and to distinguish the two of those, later you're going to want a subscript, but for right now it's probably the first one you're seeing, and I'm just going to write the capital Phi for most of this video. So the definition of flux is that it's the integral over the surface of the electric field dotted into a little piece of the area. This might be the first time you've seen area as a vector, so I'll take a minute to talk about that. First, let's talk about this formula in and of itself. So I've written an integral as part of the definition, but for most of this video I'm going to consider the case where the electric field is constant. So you don't have to know very much calculus. One of the important things is going to be that you can pretend that integral is a sum. So later on I'll use that, but for most of the video, it's not going to be calculus. You do, however, need to know the dot product. So you see there's a dot in between that E vector and that dA vector. And that's important. So this dot right here, that's important. That's the dot product. When you multiply two vectors and you get a scalar, that's called the dot product. If you haven't seen that before, you definitely want to go back and review that because that's going to be very important for this video. As I mentioned, when you multiply two vectors together with a dot product, the result is a scalar. So flux is a scalar, and it has units of, the electric field is typically newtons per coulomb, and then area would be meters squared. You can take one of those meters and make a newton meter, so a joule, so it could also be written as a joule times a meter over a coulomb, and then a joule per coulomb is a volt, so it also has units of volts per meter. As I mentioned, the E vector is the electric field, and so you also need to have some understanding already of electric field to understand this video, and it would probably help if you also had a picture in your head of how to draw electric field lines as a model for the electric field, because I'm going to use that in this video as well. dA is an infinitesimally small piece of the area, and it has a direction that's always normal to the surface, or normal is another word for perpendicular. So let's talk more about the area vector, A. So if I pulled that out of or if it weren't under the integral, or if I integrated a whole dA without worrying about the electric field, then I'd get the whole area vector. So let's consider a couple cases here. Let's try a rectangle. So the area of a rectangle, of course, is just the length times the width. Now, we just said normal to the surface or perpendicular to the surface. So in this case, the area vector would be the length times the width out of the page or out of the screen. So there I'm showing in blue on the figure a symbol. If you've never seen this before, a circle with a dot inside is a symbol that we write to mean out of the page. So I don't have to draw a perspective drawing. I'll do that a couple times today, but it's harder to see. So that symbol means out of the page. So A vector, which is shown in blue in the figure there, for that rectangle is the magnitude of it would be the length times the width of the rectangle, and then the direction would be out of the page. If you're using your standard X, Y, Z axis, where X usually goes to the right, Y goes up, then in that case the Z direction would be out of the screen. And so if we do that, then I would call that direction K hat in what we usually use I hat for X direction, J hat for Y direction, K hat for the Z direction. Let's look at a circle. So if you find the area of this circle, the way I have it drawn, so I've drawn a circle of radius r. Now this one is a perspective view. I'm trying to draw that here. I'm trying to draw it centered on the origin, and the circle itself is in the YZ plane. And so in that case, the perpendicular direction to that would be in the positive X direction, which I'm calling the I hat direction. You might be asking yourself, well, how did I know for the rectangle that it was out of the page as opposed to into the page, because that's still perpendicular, and how did I know this plus X direction for the circle instead of the negative X direction? That is something that in this pure way I've described it so far, there's no real way to tell. In very many physics problems, there is a way to tell. So I'm not going to worry about that very much right now. And the other thing that happens is when you consider a closed surface, and this also happens a lot in physics where we're looking at solid objects. And so a solid object, the surface area of a solid object is usually considered to be closed. So for example, for a sphere, let me draw it for you too. Yeah, so for a sphere, I'm going to shade it in so you can see it's a sphere and not just a circle. The outward from the surface, or normal to the surface, probably everybody already knows at this point that radius lines are always perpendicular to the circumference of a circle or the circumference, the surface of the sphere. So if you have a sphere of radius r, it has surface area 4 pi r squared, the direction out. So closed surfaces always have the direction out. Here there is a choice whether to use out or in. And in physics we conventionally use out for the plus direction. So 4 pi r squared r hat, and I've drawn some r hat vectors which would just be radius. Just like the I hat, j hat, k hat, r hat is a unit vector. That means it has length 1 and it points radially outward. And in this case, so the area vector also points radially outward, so I've drawn some area vectors on there as well. Let's talk more about, let's see, I want to back that up a little bit. Let's talk more about a special case where the electric field is constant. So when the electric field is constant, I can pull it out of that integral. So I mentioned that I would spend most of this time doing that and it wouldn't be a whole lot of vector calculus. It is, or it can be important, there's one example where you'll have to think about this in this video. It can be important to think about the dot product, the dot part and the direction part as staying inside the integral. If the surface area, like that sphere we were just looking at, all of those r hats were pointing in different directions. So even if the electric field is constant, it's possible to have the electric field, the cosine between the area vector and the electric field be at a different angle throughout the whole surface. So so think about leaving that cosine. One way of writing the dot product is magnitude of the first one, magnitude of the second one, and the cosine of the angle between them. So think about leaving that cosine inside the integral if it comes up. When it doesn't though, when you just have everything being one, like a square or a circle like we were drawing in the previous picture where the whole entire area vector is one direction and everything's constant, you can pull the electric field out of the integral and you just end up with the magnitude of the electric field and the electric field vector dotted with the area vector. So that's what we're going to work with here for a couple of examples. So example 1. A uniform electric field, E, and I write the E0 I hat to indicate that it stays the same as it started, so that E0 usually means the initial. So E0 I hat and a square of side A. Find the flux through the square when it is, so basically I'm going to put the square in different orientations for that same electric field. So find the flux through the square when it is in the YZ plane, part B when it is in the XY plane, and part C when it's tilted at an angle of 30 degrees relative to the YZ plane as shown. That's one where a picture is worth 1,000 words. It's hard to describe what that means, but if you look at a picture, here I've drawn a side view and I'm only showing the XY, so that red line is the side view of the square. And it makes a 30-degree angle with the y-axis, and Z would be coming out of the plane of the page. I'm going to draw a couple pictures here to answer the first part. So here I'm showing a perspective view where I show a picture of the electric field. So a uniform electric field is equally spaced lines representing E going the same plus X direction. And then the square for part A is in the YZ plane, which is like that circle I did a minute ago. So the area vector is perpendicular to the YZ plane, which points in the plus X direction. So that's a perspective view, and I'm going to draw the same thing with just my pure side view so that you can see a little bit easier, I think. That, again, that red line is the side of the square if I'm looking directly side on. So the flux is the electric field dotted into the area vector. If you use the components, I hat times I hat is always a 1. And so you get E0 times A squared. If you like the other definition of dot product, it's the magnitude of the first vector, which is E0, magnitude of the second vector, which is A squared, times the cosine of the angle between them. They are parallel, so the angle between them is 0, so you just get E0 times A squared. So that's the answer for the first one, E0 times A squared. All right, let's keep going. So part B was when the circle is in the square is in the XY plane. Here, it's a little bit hard to tell, but so it's in the plane of the screen. It's pretty easy to draw. And we get that the area vector, again, is perpendicular, so straight out of the page, there's my symbol indicating that it comes out. And when I write it in terms of components, E0 I hat times A squared K hat, again, K hat for out of the page, and I hat dot K hat is actually always 0. They are 90 degrees with respect to each other. So if you do by the component method, you also get 0. The cosine of 90 shows you 0, and you can see that. For part C, it was tilted at an angle, and again, I'm trying to show you a perspective view and then the direct side-on view. And that picture, I thought that picture got a little complicated, so I'm going to blow that up. And so my electric field vector is going in the plus x direction, and if the square itself is tilted down 30 degrees from the vertical, then the normal to it will also be tilted 30 degrees down from the horizontal. So that theta that I just drew in that picture, which is the angle between the electric field and the area vector, and that's what I need by the definition of my dot product, I need the angle between those two vectors, that will be the same 30-degree theta. So my flux, electric field dotted into the area, magnitude of the electric field, magnitude of the area, cosine of the angle between them, E0 A squared cosine 30. You can write cosine of 30 as the square root of 3 over 2. I like to leave radicals in there when I am using symbols. You could of course crunch that on your calculator and get 0.866 E0 times A squared. And that is the answer for part C. There's also, I wanted to talk about a model of the electric flux where you think about the flux through a surface is proportional to the number of field lines that go through the surface. So that's kind of why I was saying earlier that the field line model could be very helpful. So let's think about that model in the context of the last 3 examples that we just did, and we'll see that it's consistent. So we take case A, where the square was perpendicular to the square itself was perpendicular to the electric field, which meant that the area vector was in the same x direction as the electric field. The electric field is parallel to A, which means perpendicular to the square. It has the largest number of field lines that go through that square, in this case. In the other case, where the plane of the square is in the plane of the paper or the screen, then the electric field, none of the electric field lines actually go through the square. They're all going right along the square, and none of them actually go through the surface of the square. So that, in that case, that has a flux of 0 by that model, and that was what we got when we did the calculation. For part C, where it's tilted at an angle, I sort of try to draw the length of the red line the same as the length, so it's the same size rectangle. And the point is that when it's tilted, the top, when it was straight up and down, the top and bottom field lines just made it through the square, and now that I've tilted it at this angle for the same size, not quite maybe the same size, they don't, I've exaggerated it just so you can see, the top and bottom field lines no longer go through the square. So this one we would predict by our model would have a smaller flux than case A. And indeed, we saw that it did when we did the calculation. We got square root of 3 over 2, E0 times A. as opposed to just the E0 times A. So we expect that. It has fewer field lines going through the square than A. So that, again, it's just a model. It didn't give us an exact number, but it was consistent with our calculations that we did a while ago. Now let's consider the case of the flux through a closed surface. Oops, I need to go farther forward than this. We backed up to the previous slide. Oh, let me see if I can fix that. So, the flux through a closed surface. Remember that closed surfaces are things like the outer surface of a solid object, or you can think of it as just being a cube or a sphere. Let's start with the case of the cube. So, example 2. Find the flux through a cube of side A in a uniform electric field. The same electric field we had in the last case, where E vector is equal to E0 in the positive x direction. Recall that the area vector for a closed surface points out. So each face of the cube has an area vector that's in a different direction. And is always normal to that particular face of the cube. I'll draw a picture of this in just a second. So that n hat symbol means that anytime you see a hat vector in physics, it means unit vector, length 1, and in this case the n means normal. So it's always perpendicular to the surface and it always points out. So there, n is a unit vector, perpendicular to the surface. So draw a quick cube here and look at the first couple faces. So if we look at the right face of the cube, it has a direction, so perspective drawing again. So that's indicating that it has the, whatever A1 is the area of that face, and then in the plus x direction. Then if we look at the top face of the cube, it has an area vector that would be pointing straight up. The left face of the cube has an area vector that would be pointing to the left. So that is the negative I hat, negative x direction, which gets a negative I hat. So A3 in the negative I hat direction. And then the bottom face of the cube similarly is negative j hat because it's pointing down. I thought it was a little too messy to draw the front face and the back face on the cube, so I'll just say the front face has an area vector that points out. Again, it's outward direction, points out of the screen or out of your page, and the back face has an area vector that points into the page, which would be the negative k hat direction in the notation we've been using. Flux is the integral of E dot dA. So for the cube, everywhere the electric field again is constant. So the E0 dotted into the x hat is, the E0 times the I hat is in the same direction every single time. But each of those 6 faces of the cube, of course, has an n in a different direction. You saw we had a plus I hat, a minus I hat, a plus j hat, a minus j hat, a plus k hat, a minus k hat. So I have to treat this integral as a sum for each one of those different directions of A. So I'm going to write all of those pieces separately. So if I consider just the exact first one I wrote down that I called A1, which was the right face of the cube, you get E0 I hat dotted into A1 I hat. Then consider the next face of the cube that I did, which was A2, and you get that E0 I hat dotted into minus A2 I hat. That was the one that was pointing to the left. Then we do the top face of the cube, and oh, I just realized I have either the wrong, whoops, I mixed up which ones I called the A2 and A3. Let me see if I can fix that for you. So let's see, this A3 is really that's the one that is pointing up. So that is really an A2. Let's see if we can fix that. Yep, that's the A2 j hat, and this one back here, I hope I didn't do that for the rest of the faces. I might have. This one back here was actually the third one I did, so it is the A3 should be there. Let's see if that fixes it. Yep, okay, and then let's see, this one would be A4, I hope. That's hopefully is what I had matching over there. Yes, that one's an A4, and then the outward face should be the A5 this time. Yes, I got those right. So the E0 I hat dot E5 K hat for the front face, and E0 I hat dotted into minus A6 K hat for the back face. All of this has come up before, that I hat dot I hat is 1. I hat dot J hat is 0, and I hat dot K hat is also always 0. So most of those terms, the last 4 terms, are going to go away because there's an I hat dot J hat, so that's a 0. There's an I hat dot J hat again, and an I hat dot K hat, so those last 4 terms all go to 0. And even though I called them A1, A2, A3, A4, A5, A6, that was only so that you could tell which face I was looking at, which is why it's important that I have the right numbers matching the right one, so you can tell which face is which. But I made it a cube so they all have area A squared. So when I evaluate, all of those 4 terms go away. The first term is an I hat dot I hat, so it becomes E0 times A1. And the second term is another I hat times minus I hat, so that gives me the minus sign there, minus E0 A2. But again, as I said, they both have area A squared, so it becomes E0 A squared minus E0 A squared. So the flux through that cube, because of a uniform electric field, is 0. That matches with our electric field line model, although you do have to do a special thing where it turns out it matters that the field lines go in one side and out the other side. So the convention is that a field line going into a surface gets a minus sign, a -1 count, and a field line going out of a surface gets a +1 count. So for the special case of a closed surface in a uniform field, the flux is always going to be 0, because each field line goes in, giving you a count of -1, and each field line, if it's a closed surface, each field line must come out somewhere, and so that gives you another count of +1. So for each line, there's at least 1, +1, and -1, and they cancel out so that the total is 0. That's what we saw for the cube, but it turns out it works for even a really funky surface like this one I've drawn here. So even if you imagine that's a solid object, just consider 2 of our E field lines that I drew earlier. There's a point where it goes into the surface, so that gets a -1 count. There's a point where it goes out of the surface, so that gets a +1 count. If you do the same thing for the top line, there's an in, that gives you a -1. There's an out, that gives you a +1. There's another in, which gives you a -1, and another out, which gives you a +1. So every line that goes in must also come out for a closed surface, so you constantly get a total of 0. The number in always must equal the number out. So for a closed surface, you get a flux of 0. I will end this video here. There is a lot more to say about flux. You're probably going to see it again in Gauss's law. The flux, again, through a closed surface is about half of Gauss's law. So you'll probably get another chance to practice that coming up soon.